All right, today we're diving into a research proposal that connects two worlds you've probably never thought of together, the chaotic symphony of a rainforest and the clean, simple clicks of Morse code. It's a fascinating link, and it's all thanks to a really cool field called ecoacoustics.
So, let's just jump right into it. What on earth could a forest packed with birds possibly have in common with Morse code? I mean, on the surface, they're like total opposites, right?
On one hand, you've got this wall of sound, an entire ecosystem buzzing with life. Scientists even have a cool name for it, biophony. And on the other hand, a super simple man-made signal, just dots and dashes. But here's the kicker. Believe it or not, they actually share the exact same fundamental challenge.
Yeah, that's right. Noise. It doesn't matter if you're an ecologist out in the jungle trying to count bird species by their calls, or you're a radio operator trying to pick up a faint message. Your number one enemy is always the same thing. How do you pull a clean, clear signal out of a whole mess of background noise? And this is where things get really interesting. See, researchers in ecoacoustics have spent years building these incredibly sophisticated tools to solve this exact problem, but for nature. And that's where a researcher named Matthew Younger comes in. He was looking at all this work and, well, he had a light bulb moment.
He's thinking, wait a minute, if these methods are powerful enough to pick apart the sound of an entire forest, couldn't we use them for something way, way simpler, like the dits and dahs of Morse code? It's a brilliant question. So let's take a look. What's actually in this ecoacoustic toolkit he's talking about?
Okay, so the big first step for these ecoacoustics folks is a total shift in perspective. They decided to stop just listening to the world and to start seeing the sound.
And how do they do that? With something called a spectrogram. It basically turns raw audio into a picture. Time goes one way, frequency goes the other, and the brightness shows you how loud it is. Suddenly, you can literally see the patterns and rhythms in the sound. But, a picture is great, but it's not data. They needed a way to actually measure what they were looking at.
So, they came up with something called the Acoustic Entropy Index. You can thank a researcher named Jerome Sewer and his team for this one, and it's so smart. It basically boils down all that chaos into a single number that tells you how orderly or disorderly a sound is.
And here's how to think about it. Imagine a pure, clean tone, like a single Morse code dit. It's super predictable, very orderly. Its entropy score would be way down near 0. Now, think about pure static, just white noise. It's completely random and chaotic. Its score, way up near 1. See? All of a sudden, you have this really elegant mathematical way to measure how clear your signal is. Okay, so that's great for measuring overall chaos. But what if you need to separate different kinds of sound from each other? I mean, that's what ecologists have to do all the time. How do you pick out a bird song from, say, the constant hum of a nearby highway, what they call anthrophony?
For that, there's another tool in the box, the Acoustic Complexity Index, or ACI. This one is really clever. It's designed to ignore steady, constant sounds, like that highway hum or static, and instead, it hones in on sounds that change a lot, sounds that are dynamic, like bird songs. It's basically looking for variation.
But the coolest tool, the most creative one in the whole set, actually comes from a field you would never, ever expect: geography.
Yeah, geography. So you know how geographic information systems can look at a satellite photo and automatically identify things? Like, that's a forest, that's a lake, that's a city. It does this by analyzing their shapes and textures. The technique is called Object-Based Image Analysis, or OBIA for short.
And here is the absolute genius move. A team led by researcher Yelin Zhao asked, what if we did the exact same thing with a soundscape? What if we treated a spectrogram not like a graph, but like a map, a landscape of sound?
So instead of just numbers, they started treating each little bird call as a syllable patch on the sound map. The computer could then identify these patches based on their visual shape, size, and texture. And the results were insane, like over 93% accuracy in picking out bird sounds in super noisy city forests. They basically turned a really hard audio problem into a computer vision problem, which we're much better at solving.
Okay, so with this incredible toolkit in mind, seeing sound, measuring its chaos, and mapping it like a landscape, let's circle back to Matthew Younger and his big idea.
His hypothesis was pretty straightforward. If these tools are sophisticated enough to untangle the absolute chaos of a forest's chorus, then they should be more than powerful enough to analyze something as simple and structured as Morse code, right?
And so his research plan is basically to take this whole ecoacoustic playbook and just apply it step by step. First, visualize the Morse code as a spectrogram. Next, use those acoustic indexes, H and ACI, to score the signal's clarity. And then, the really cool part, use that object-based image analysis to identify the dits and das as if they were little shapes on a map. The whole point is to see if this method could be a more robust way to analyze the signal, especially when you're dealing with messy, real-world noise.
So when you step back, this whole thing isn't really just about birdsong or Morse code. It's about something much, much bigger.
It's about the fact that sometimes the most amazing solutions aren't new inventions at all. They come from borrowing a tool that was built for one problem and applying it to something completely different. By looking to the forest, Younger found an entire toolkit that was already built, already field-tested, and saw how it could offer a totally fresh perspective on a classic problem. It's just a fantastic example of scientific creativity in action.
And really, that's the big takeaway here. It kind of makes you wonder, right? What huge problems could we solve right now if we just borrowed some ideas from a totally unexpected place? What expert toolkit from another field could be the key to unlocking a breakthrough in yours?